Welcome to Chem 112, Practice Exam 1C. Okay, in this first question, we're asked to figure out what the identity of X is in the nuclear reaction given. So, I'm going to enhance this, make it a little bit larger. Enhanced. So, in this problem, we're trying to find, well, we need to know what isotope X is, so we're trying to find, I'm going to call that Y. But also, we need to figure out what element this is. I'm going to call that Z, so what atomic number it has. In order to answer this question, we also need to consider how many protons each of these other chemical species has. So we're told the alpha particle here has 2, classic alpha particle move. Iron, if we look it up on the periodic table, is element number 26, so it has 26 protons. Hydrogen is element number 1, so it has 1 proton. Now we have all the numbers we need, and we just need to keep in mind that all of the atomic numbers, i.e. the subscripts down here, need to add up on the left-hand side and the right-hand side of the equation. And all of the total masses, the total numbers of nucleons, the superscripts need to add up as well. On the left-hand side and the right-hand side, they need to be equal. So first, let's figure out what element we're looking at. So we're going to solve for Z. And Z plus 2 is equal to 26 plus 1. So what we'll do is subtract 2 from both sides. We'll end up getting that Z is equal to 25. So 25 protons means that we're looking at none other than manganese, Mn. Now we're going to do the same thing with the superscripts. So for the superscripts, we have on the reactant side 56 plus 2, and we're going to set that equal to Y for a mystery isotope, plus 4, and we'll solve for Y. We'll get Y is equal to 54, and mystery solved. Our new isotope is manganese 54. In this question, we're trying to find out the most likely form of decay of cobalt-60. So the first thing we need to do is ask ourselves, is cobalt, is the number of protons in cobalt greater than 83? No, it is decidedly not. Cobalt is element number 27, so this is not going to be a great candidate for alpha decay. So we're going to rule out alpha. But now we need to look at our radioactive isotope, which is, in this case, cobalt-60 that we're analyzing. And what we want to do is compare it to the most stable isotope. So cobalt, by virtue of being cobalt, again has 27 protons in it. Now, we're going to consult the periodic table to figure out what the most stable isotope of cobalt is. Remember, the atomic weight that appears on the periodic table is skewed toward the most stable, the most abundant isotope. So for cobalt, the atomic weight of cobalt is 58.933, so we can round that to cobalt 59. So our most stable form of cobalt is cobalt 59, which again, by virtue of being cobalt, has 27 protons. So now we want to ask ourselves, what is wrong with our radioactive isotope? So again, both of these have 27 protons. So we're going to check to see the number of neutrons they each have. So cobalt 59 has 59 minus 27, or 32 neutrons. Whereas cobalt 60 has 60 minus 27, or 33 neutrons. So, now the question is, what is wrong with our radioactive isotope? Are there too many or too few neutrons? Well, there's too many neutrons. Too many neutrons means this is a great candidate for beta decay. Beta decay, remember, turns a neutron into a proton. So this is going to be beta decay for the win. This question asks us to identify what the transition states are, / activated complexes. So when looking at a reaction profile diagram, remember the transition states / activated complexes, so the TS's / activated complexes, the ACs, they are the relative maxima. So they are here and here. So in this case, it's choice B, yet again, is our answer. But let's go through and label everything else on this diagram. So whatever we start with, those are our reactants, our starting materials. whatever we end with, those are our products. So A, our reactants, E, our products, and then finally, any valley that we happen to run into along the way, that we encounter along the way, these are intermediates. So C right here would be an intermediate. This question asks, which of the following statements regarding nuclear decay is true? Statement A, the half-lives of radioactive nuclei can be shortened significantly through increased temperature, concentration, and catalysis. Well, no, that's going to be a big old brant. We cannot do anything to change the half-life of decay. That's why nuclear waste is a problem. If we could speed it up and get it decayed faster with them, we wouldn't have to store it in places. So this is not true. For nuclear decay processes, it's only dependent on what isotope we're looking at. B, nuclear fusion is when large nucleus split into 2 or more small nuclei and 1 or more neutrons. Well, once again, that's going to be a big old So this is not fusion that this is describing. This is fission that this is describing. Fission is blasting apart a nucleus. Fusion is when smaller nuclei fuse together. Choice C says nuclear decay kinetics are second order. Nope. Nuclear decay kinetics are always first order. So if this was first, then that would be right, but it's not, so this is false. Choice D says beta decay results in a net increase of nuclear charge. So recall that beta decay is the conversion from a neutron to a proton. If we're converting a neutron to a proton, that means that our nucleus is going to have 1 greater positive charge. Because protons are positively charged, neutrons are neutral. So, net increase of nuclear charge, I like this one. Ding! Indeed. And then E says positron emission and alpha decay both result in a net increase in number of neutrons in a nucleus. That's not true. Positron emission does, because positron emission turns a... So positron emission is the opposite of beta decay. It turns a proton into a neutron. However, alpha decay are emitting alpha particles, which have 2 protons and 2 neutrons. So alpha decay would result in a decrease in the number of protons and the number of neutrons. So this question asks us to consider a forward reaction and a reverse reaction, an elementary step, one-step reaction. So drawing a diagram is really, really helpful for understanding a problem like this. So I'm going to make a little reaction progress diagram where we have energy plotted on the y-axis, and we have reaction progress on the x-axis. And now first let's draw out the uncatalyzed reaction. So to draw this out, I'm going to just kind of mark this area here as my reactants. We can see this has a negative. This says delta H. This actually should technically be delta E, though, because it's more free energy that we're looking at, not just enthalpy. And the products are lower in energy, so I'm going to put a little mark there. And now what I'm going to do is make a little line for our reference here. And then I'm going to draw in, so I've got an activation energy of 30 kilojoules. And then the iPad slipped there. Okay. So this is a rough sketch of our diagram. And again, our energies that are associated with this are, our delta E is negative 15 kilojoules. Now, I want to point out, I don't like to put the negative sign here. We can tell that if we're going in the forward direction, that it is a net decrease, and it would be negative for our energy change. So the reason why I don't like to put the negative sign there is it's all relative as to which direction we're going. If we're doing the reverse reaction, which is what we're ultimately going to analyze here, then it's going to be positive 15 instead. So I just like to write the magnitude. And let's write out the magnitude of our activation energy. It is 30 kilojoules per mole. Okay, so now what we're going to do is I'm going to draw out a diagram for our catalyzed reaction. It tells us that it lowers the activation energy by 10 kilojoules per mole. Now we're starting with the same reactants and ending with the same products. A catalyst does not change that. All it does is decrease the activation energy. So we'll end up with a curve like that. Make it look a little bit nicer. Okay, so we were told that it is 10 kilojoules lower than the regular uncatalyzed reaction. So 30 minus 10, that's going to be an activation energy for the catalyzed forward reaction of 20 kilojoules per mole. Okay, now we have everything we need. So if we're looking for the energy of the reverse catalyzed reaction, we're looking for the activation energy of the reverse catalyzed reaction. We can see here that for reversing the reaction, we're going to start here. We have to first overcome these first 15 kilojoules to get back to our baseline, and then another now 20 kilojoules more to get up to the top here. So I think this diagram is really useful in seeing how much energy we need to overcome in the reverse direction. So it's going to be 15 kilojoules plus the 20 kilojoules, which gives us a total of 35 kilojoules per mole. All right, we have another true-false question. So which of these statements are true regarding enzymes? 1, enzymes make a reaction more favorable by lowering the energy of the products. No, we still have the same products. They still have the same inherent chemical potential energy. That is false. 2, enzymes increase the KEQ of a reaction. So this is implying that enzymes allow us to create more products. They make a greater product-reactant ratio. This is also not true. Enzymes do not do anything to change the relative amount of products to reactants at equilibrium. All it does is speed up the rate at which we get to equilibrium. So that's also false. Enzymes lower the activation energy of a reaction. I like that one. Indeed, they do. Lowering the activation energy makes reactions go more quickly. And it says enzymes can increase the Arrhenius factor or frequency factor A of a reaction. This one is also true. Enzymes can hold molecules in place more favorably to collide with the proper orientation, which can allow the reaction to proceed more quickly. So 3 and 4 are the only true statements here. So this question wants us to figure out what the units of the rate constant are given a rate law. And the rate law appears right up here. There's 2 ways you can do this. You can always go about figuring the units of K by doing a dimensional analysis. And what I mean by that is rate is always going to be in molarity over time. Often in these problems, we'll just say seconds for an arbitrary unit, but it could also be presented in per minute, per hour, per day, per year, per century, etc. So molarity per time, and it's equal to some rate constant K. So this is our rate value here. Again, we're just doing a purely dimensional analysis, so we're not going to be putting in numbers. We don't need numbers to answer this question. So the rate is equal to some constant K, and then our first reactant, nitric oxide, is the second order. So I'm just going to put molarity in here because that's how we measure concentration. So it's going to be molarity squared. And then chlorine, again, we would measure that in terms of molarity. Okay, so now let's simplify this a little bit. Molarity squared times molarity is equal to molarity cubed. So we end up getting Km to the third is equal to molarity times seconds to negative 1. And remember, we can also just say, since this is just regular molarity, we can also call this molarity to the first. So now, in order to solve for K, to figure out the units, we'll divide both sides by molarity cubed. And when we do, we'll end up getting, so molarity to the first divided by molarity cubed is going to be molarity to the 1, that's from here, minus the third. So just using the rules of powers here, dividing by powers. So we end up getting molarity to the negative 2, and then S to negative 1. That's still consistent. And there we have our units. The other way that we can think about this is there's a pattern that arises if we look at orders. And that pattern is as follows. So this is second order with respect to nitric oxide and first order with respect to chlorine. So this is third order overall. And you'll see a pattern that develops where if we look at the order of a reaction and the units of K, Okay, so if something is, let's go through and do 0th order, 1st order, 2nd order, 3rd order, and 3712th order, because, you know, why not? If something is 0th order, the units of K are just molarity per second. If something is 1st order, it's just time to the -1. Seconds, minutes, doesn't matter. Again, I'm just using seconds here, but it could be any unit of time. Another way you can think about this is molarity to the 0th, because any number to the 0th is just 1. Okay? So we have molarity to the 1st, seconds to the -1 for 0th order. Molarity to the 0th, seconds to the -1 for 1st order. 2nd order is m to the -1, s to the -1. 3rd order is m to the -2, s to the -1. And 3712th order is going to be, well, molarity to the -3711th. It's just basically whatever order it is, minus 1, so it's going to be negative that. And then seconds to the -1. So the most common orders that we usually look at in this class are 1st order and 2nd order. We've analyzed them more deeply. And then 3712th order. Lol, JK, not really a thing. But just kind of some hyperbole to show this rule of thumb. Okay, this problem wants us to figure out what orders each reactant is, reactant A and B, in a reaction. So first things first, it says that changing the concentration of B has no effect on the results, on how fast the reaction is going. That is classic what order? 0th. Doesn't matter what we do to B, we could double it, we can triple it, we can make it 100 times as concentrated. It is not impacting the overall rate of the reaction. We would need it for the reaction to go, but it doesn't have any bearing on how fast the reaction proceeds. Now then, with substance A, we have to delve a little bit deeper. So we're told that with A, in 33 minutes, it's 50% consumed. Then after a total of 66 minutes, it's 75% consumed. So what I like to do is write out a little bit of almost like a timeline of what happens here. So we start off with A, and we have 100% of our reactant A. And then it tells us that it takes 33 minutes for it to be 50% consumed. So we would have 50% remaining. After, again, this takes place over a period of time of 33 minutes. Okay, so what do we call that? The time it takes to use up half the reactants. That is a half-life. So one half-life took 33 minutes. Now then, it tells us that it takes a total of 66 minutes for A to be 75% consumed. So for it to go from 50% of the original concentration down to 25% of the original concentration. So if we consider that this whole elapsed amount of time here is 66 minutes total, we can reason that the amount of time it took to go from 50% down to 25% is, well, 66 minutes minus the first 33 minutes. Guess what? This was 33 minutes yet again. So, once again, this is a subsequent half-life because it's the time it takes to use up. We had 50% of the original amount, and then we went down to 25%, so that's half of the half. So this was a subsequent half-life. And what do we notice about the time of each half-life? Well, they're consistent. Each half-life was 33 minutes. Consistent half-lives are a hallmark of first-order reactions because for first order, half-life is equal to 0.693 divided by K. It's only dependent on the rate constant, which is a constant for any given reaction at any given temperature. So for first order reactions, each subsequent half-life is the same amount of time, and that is unique only of first order reactions. So that means this has to be first order with respect to A. So it's first order with respect to A and 0th order in B is our answer because of those consistent half-lives. In this problem, we are, in addition to Penn's state, constructing a rate law. So there are two ways of coming up with a rate law, both of which are on this practice exam. One way is through a mechanism, another one is through a table of data. We'll cover that later. And remember, whenever you have a mechanism, the most important step for determining the kinetics is the slow step. Because everything bottlenecks at the slow step. It's kind of like traffic. Oftentimes, the amount of time it takes to get from one place to another are dictated by the amount of time that you spend stuck in traffic. So this is kind of like the traffic step of this particular reaction here. Because a reaction can only proceed as quickly as its slowest step. So, given that we have a mechanism, a step-by-step breakdown of the reaction, we can write a rate law based on this. So it's going to be rate is equal to some constant K, that's classic. And then we base it off of whatever is reacting in the step. So it's N2O2 times H2. And this is technically accurate, but is it a good rate law? The answer is written right here. The answer is no. No, it is not. Why is this not a good rate law? Because if we consider what we have in here, our rate law contains N2O2, which was made in one step and then used in a subsequent step. It is an intermediate. And can we have intermediates in a good rate law? Well, once again, to recycle this joke, no, we cannot. But in the words of the great poet and philosopher John Bon Jovi, whoa, we're halfway there. We have a working rate law. Now we just need to use this first step up here and the fact that any step preceding a slow step will reach a fast equilibrium. So while the slow step is slowly going and taking its time, the first step has a chance to reach equilibrium, where the forward rate and the reverse rate, how do they relate? They're the same. And that's the fact that we're going to capitalize on here in order to come up with our rate law. So what I'm going to do is write a rate law for the forward reaction, that first step, that fast step. So Kf, just some arbitrary rate constant, times, and then it's NO times NO. I can just simplify that, make it NO squared. And that's going to be equal to, for our reverse reaction, so there'd be some rate constant K sub R, we'll call it, for reverse, times the N2O2. And what our goal is, mathematically, is to solve for N2O2. Because once we solve for it in terms of reactants or catalysts, all we have to do is substitute in our working rate law, and then we're done. So I'm going to divide both sides by K sub R to solve for the concentration of N2O2. Any constant divided by itself is just 1, and a constant divided by a constant is just a whole new constant. Doesn't matter what it is. I'm going to call this K pi because it's arbitrary. We're not solving for it here. It's just a constant. Now we've done basically all the work. We just need to substitute in this for our intermediate because they're equivalent. So we get our overall rate law, which is going to be rate is equal to a constant times a constant. What is that? Well, again, it's just another constant. We don't care what it is. Oftentimes you'll see it called KOBS for observed, but it doesn't matter. Our answers don't have the OBS here. And then the NO squared. So I'm going to write NO squared. And the H2 remains untouched. And now we have a good working rate law. So the answer is choice A. In this problem, we first have to figure out what order this reaction is. So we're given two different graphs. In one, we're plotting the natural log of concentration versus time. The other, we're plotting 1 divided by concentration versus time. And the key here is to look for which one gives us a linear relationship. As we can see here, in this first plot, all these points are lined up nice and in a row. That is not the case with the one divided by concentration versus time, where we have more of a curve. So we can say definitively, this must be first order, because these data adhere to a linear trend that follows this equation right here, the first order integrated rate law. The other thing that we can glean from this graph, if we look at the slope is equal to negative k. So we can say that we're given the slope here is negative 0.006 seconds to negative 1. So we can just say k is equal to 0.006 seconds to negative 1. Now then, we're asked if we start with 3.2 molar and we allow 500 seconds to elapse, how much will be remaining? So we have an initial amount, we have a rate constant, we have a time. We can plug everything into the integrated rate law. And there are two different versions that we can use. The one is written over here on the right. I personally prefer to use this version of the integrated rate law. Oh, either one will work. I just prefer this one because it consolidates the terms a little bit more. So I'm going to plug in the values that we have into our first order integrated rate law. And actually, honestly, what I like to do is I like to just keep this as a sub t divided by a sub 0 and then plug in the initial amount at the end. So I first like to solve for the fraction of reactants remaining before plugging in the actual value itself. So we have the natural log of a sub t divided by a sub 0 equals negative k, 0.006 seconds to negative 1, times our time, which is 500 seconds. When we multiply these out, our units align, so seconds. So our units are good here, so we can cancel out seconds times seconds to negative 1. They'll just cancel out. And what we're left with is the natural log of a sub t divided by a sub 0 equals negative 3. Now to get rid of that natural log, what can we use? An axe. Haha, get it? Like natural log. Zing! All right, we can use E, Euler's constant. And that's going to effectively cancel our natural log and give us our ratio of a sub t to a sub 0. So we end up getting that a sub t divided by a sub 0 equals 0.0498. So what this tells us is that there are 4.98% of the initial reactants remaining. But we want to solve for the actual amount, so that's easy enough. All we have to do is plug in our a sub 0 now. Oh, there it is, 3.2 molar. We'll multiply that through and solve for a sub t. So a sub t equals 0.160 molar. Okay, in this question, we're trying to relate an initial amount, this 20 microliters per milliliter. We're trying to relate an elapsed amount of time. So starting at 1 p.m., ending at 11 p.m., 10 hours have elapsed, and we're trying to relate it to half-life K. So once again, this is going to be a case where we have the first order integrated rate law to the rescue. And we can tell this is first order because we're told that, well, it's first order. So what do we know here? We know that time is, if it goes from 1 o'clock to 10 p.m., it's 10 hours that have elapsed. We also know our half-life. The half-life for this particular clearance is 3.2 hours. Now remember, if you know the half-life for first order kinetics, you can directly relate half-life and rate constant K. In fact, we have an equation on our data sheet that combines this equation and the integrated rate law together. I personally like to solve for K and then plug it in, but if you'd prefer to use that version, that's perfectly fine too. So our rate constant K is 0.217 hours to negative 1. Now we can plug in to our first order integrated rate law. Again, I like to solve for the ratio a sub t divided by a sub 0 before plugging in a sub 0. So I like to take this kind of one step at a time. But you don't have to do that. You could plug it in now if you wanted to. That's perfectly fine too. So we have negative 0.217 hours to negative 1. And our time here that elapses again is 10 hours. So we make sure our units match up, and indeed they do. Hours will end up canceling out, and we get the natural log of a sub t divided by a sub 0 equals negative 2.717. Okay. So then once again, to get rid of that natural log, we'll use Euler's constant. That will cross that out, and we'll end up getting that a sub t divided by a sub 0 equals 0.114. So if we're asked what percentage will be remaining after these 10 hours, it would be 11.4%. But we're not asked that here. We're asked to find the actual amount. So now I'm going to plug in my a sub 0, which, the units are a little bit funky here, but doesn't really matter. So our a sub 0 is 20 microliters per milliliter. And then I'm going to multiply that through, and we'll end up getting our answer, which is 2.28 microliters per milliliter. So choice C. All right, Dr. Julius Anti-Haber is a scientist that wants to turn ammonia into elemental components, hydrogen and nitrogen. You see, it's funny because it's the opposite of the Haber process. So, Julius Anti-Haber, cute. Okay, so here's what we're going to do. We want to find here the average rate of disappearance of ammonia over the first 45 seconds of the reaction, given these two cartoons. So what we're going to do is we can look at the amount of ammonia that disappeared. So our final amount of ammonia, we have 2 of these molecules in here. So, and each one represents 1 molar. So our change, our final amount is 2 molar. Our initial amount was 4 molar. And this all took place, if we wanted to make this a rate, we have to put it over time, right? So this all took place over 45 seconds. Okay. So we had 2 molar disappear over a span of 45 seconds. And the negative sign that we have here, that's just because our change was negative. Just remember, rates are always reported as positive values. So our rate is not actually going to have a negative number in it. You just say the rate of everything is relative to if it's appearing or disappearing. So we would just say that it's 2 molar that disappeared over 45 seconds. So now let's simplify this and see what we get. This ends up being 4.44 times 10 to the negative 2 molar per second, our choice E. Okay, in this question, we're looking at the decay of a radioactive isotope. We're told it has a half-life of 73.8 days, and we're asked for how much will remain in the body after 1 year has passed. Wait a minute. Look at these. We have a units discrepancy. 73.8 days is our half-life. 1 year. Let's do some conversions here. So, 1 year is equal to 365 days. Now, everything is nice and in appropriate units. We can plug into, once again, our old friend, the first order integrated rate law. Remember, all nuclear decay is in first order. All right, so I'm going to calculate K. Once again, you could also use the form of this equation that plugs in, instead of negative KT, it's negative 0.693 times T over half-life. That works perfectly well too. I just like to solve for K for consistency's sake. So K is equal to 0.693 divided by our half-life, which is 73.8 days, which gives us 0.00939 days to negative 1. Remember, with the first order integrated rate law, with any rate law, you can use any unit of time as long as you're consistent with your units. So now I'm going to plug in to our integrated rate law. So we have the natural log of a sub t divided by a sub 0, or n sub t divided by n sub 0. And remember, this represents, so this a sub t divided by a sub 0, this is the fraction of reactants remaining. This is what we're trying to find. Well, we're trying to find the percentage. So once we find that, all we'll have to do is multiply by 100. It's equal to negative K. So negative 0.00939 days to negative 1 times our T, which is 365 days. All right. Days times days to negative 1. This cancels out. So with the natural log of a sub t divided by a sub 0 equals negative 3.43, and then we'll do e to both of these powers to give us our ratio. So we get a sub t divided by a sub 0 is 0.0321. 0.032. So if we turn that into a percentage, just multiply it by 100, we end up getting that this is 3.2%. Okay, in this problem, we're looking at the Arrhenius equation, specifically in graph form. So the way that this plot is made is, if we look at the Arrhenius equation, natural log of K is equal to negative activation energy divided by RT plus the natural log of A, our frequency factor. Now, then somebody came along and they were a graph enthusiast, squeal with delight, woo! They said, for they saw that this is, in fact, in slope-intercept form. We just have to throw in this phantom 1 here. So multiplying this by 1 doesn't change the actual math of it. And then this matches y equals mx plus b, slope-intercept form. So if we plot the natural log of k on the y-axis, and we plot 1 divided by temperature on the x-axis, if we look at this, what does our slope equal? So our slope of this plot is equal to negative activation energy divided by R. So all we actually have to do here is take our slope, which we're told is negative 3,412 k to the negative 1, and, oops, sorry, not k to the negative 1, just regular old k. And now all we have to do is set that equal to negative activation energy divided by R, 0.008314 kilojoules per mole Kelvin. So we'll multiply negative 0.008314 kilojoules per mole Kelvin by both sides, and we'll get our answer, which is 28.4 kilojoules per mole. Cool. Okay, in this problem, we are doing something called uranium-lead dating. And basically the way this works is it goes off the decay process that uranium-238 decays into lead-206. Okay, so I really like to draw a little cartoon to help me with this type of problem. And so what we're going to do is we're going to look at the rock that we have. It consists of 5.51 milligrams of uranium and 1.63 milligrams of lead-206. So I'm going to draw part of a rock here, 1.63 milligrams, and this is of our lead-206. And the rest of the rock is going to be uranium. Make it glowing. It's uranium. So this is 5.51 milligrams of uranium. Now then, in this problem, remember, whenever we look at integrated rate laws, nuclear decay, nuclear decay always adheres to first order kinetics. But also, the star of the problem, whenever we use an integrated rate law, is our reactant. So uranium is the star here. So we actually know right off the bat that our N sub T is equal to 5.51 milligrams. Because that's the amount of uranium that's remaining. Our goal in this problem is to figure out what N sub 0 is. That is the key to this problem. So let's think about this. Now, back in the proverbial day, this 5.5 milligrams of uranium that we have. So this uranium right here. Has it always been uranium? Well, yeah, we're looking at the decay of this uranium rock. So this is old school uranium. It was uranium before uranium being uranium was cool. It's hipster uranium. So voila. At time 0, this is time 0. It was 5.51 milligrams of uranium. It's still uranium. It has not decayed. Our goal then is to find out what the mass of lead was when it used to be uranium. Now, does lead-206, wink, wink, have the same mass as uranium-238, the same molar mass as uranium-238, wink, wink? No, it doesn't. However, we can just use a mole ratio here, a mass ratio rather. So we know that we have 1.63 milligrams of lead 206. And technically speaking, we could convert this into grams, and then grams to moles. And then we know it's a 1-to-1 molar ratio, because for every 1 mole of uranium you have, it decays into 1 mole of lead. And then we can turn that into grams of lead, and then grams or moles of uranium, and then turn into grams of uranium, and then milligrams of uranium. It's not necessary. We can just use the mass ratio here to make our lives easier. So for every 206 milligrams of lead 206, how many milligrams of uranium 238 would that be? So how many milligrams of uranium 238? Well, 238. Right, because lead 206 is about 206 grams per mole. Uranium 238 is about 238 grams per mole. So we can make our lives easier just by doing this. And milligrams of lead 206 cancels out. We end up getting 1.88 milligrams of uranium 238. So now our mystery is solved. That lead, back when it used to be uranium, was 1.88 milligrams of uranium. So that 1.88 milligrams of uranium turned into the 1.63 milligrams of lead that we have today. So now to get n sub 0, all that we have to do is take the amount that is still remaining. So let's just circle this one here and add it to what we figured out the lead used to weigh back when it was uranium. So let's add those together. So total, it's 7.39 milligrams. Now let's plug everything into our integrated rate law. And our integrated rate law, recall, is the natural log of however much we're left with. So our natural log of n sub t, which is the 5.51 milligrams remaining of uranium, divided by, it was originally 7.39 milligrams, equals negative kt. Oops, I haven't solved for k yet, but that's easy enough to do. So we know that k is equal to 0.693 divided by half-life. So divided by 4.5 billion years. It's a large number. So this ends up giving us that k is equal to 1.54 times 10 to the negative 10th years to negative 1. So we can plug that in for our k. And that's exactly what we're going to do. And then we're solving for t, trying to figure out how old this rock is. So the natural log of 5.51 divided by 7.39 is negative 0.294. So now we'll divide both sides by our rate constant, like so, and we will get our answer. So t is equal to 1.91 times 10 to the 9th years. Our choice A. Okay, in this problem, we're trying to find the value of the rate constant K. And the information that we're given is we're given a concentration of our bromobutane, and we're given a rate. We're also told, so this is an SN1 reaction. And the key thing that we want to focus on is that this means that the reaction is first order with respect to 2-bromobutane. So we could write a rate law based on this. Rate is equal to some constant K times C4H9Br. Cool. And now, let's see what we have. Do we know a rate? Check. Do we know a concentration? Check. That means we can solve for K, and that's exactly what we're going to do here. So I'll plug in a rate, which is 0.016 molar per second, is equal to K, which is what we're solving for, times the concentration of the C4H9Br, which is 0.31 molar, divide both sides by the 0.31 molar, and we'll get our answer, which is K equals 0.052, and well, we've got molar and molar, so this ends up canceling out, and we just get seconds to -1. Okay, in this problem, we're trying to find mass defect of iodine 127. So, iodine 127, let's take a closer look at our atom in question. So, iodine 127. Iodine, by virtue of being iodine, has 53 protons. So, iodine 127 must have 127 minus 53 neutrons, which is going to be 74 neutrons. Okay, so now we have the case of the missing mass of mystery. We're going to try to figure out how much the actual mass that we're given up here deviates from the expected mass if we add together the sums of the masses of the protons and neutrons. So what we're going to do is, first let's figure out what we would expect this to weigh. There are 53 protons, each of which has 1.00727765 AMU. And this is one time in the course where I would advocate using just a ridiculous number of significant digits, as many as possible. Plus, there are 74 neutrons, and each neutron has 1.00866649 AMU. Both of those values can be found on your data sheet. So when we do that, we'll end up getting that the total mass that we would expect from 53 protons and 74 neutrons is 128.02685571 AMU. Now hold the phone here. This number, these numbers don't match. Whoa, some mass is missing. So let's figure out how much mass is missing. So delta M, our mass defect, is going to be equal to the observed mass of iodine 127, the 126.904473 AMU, and we're going to subtract from that the calculated mass that we would expect given the number of protons and neutrons. So we're going to subtract from it the 128.02685571, and that's going to give us our delta M, which is negative 1.12238841 AMU. So that's the amount of mass that's, quote, missing. Did we just violate the law of conservation of mass and energy? Well, no, because that matter was actually converted into energy, the strong force holding together the nucleus. So this was converted into energy. Now notice our answers are given in terms of grams. This is in AMU, so we'll just do one quick conversion factor. For every 1 gram, there are Avogadro's number, 6.02 times 10 to the 23rd AMUs, which ends up giving us our answer, which is 1.86 times 10 to the negative 24th grams. And no, that is not a ton of mass, but that is the amount of mass missing from one measly iodine 127 nucleus. Okay, everybody. So in this particular problem, we need to come up with a rate law. Remember, there's 2 different ways we can come up with a rate law. We can either look at a mechanism, or we can look at a table of data. So here we have a table of data. And the way that I always start these problems is I write a generic form of a rate law. So rate is equal to some constant K, and then reactant A to some power, and B to some power, and C to some power. And our goal is to see how changing the concentration of each of these reactants will change the overall rate. And so what I mean by that is, for example, with experiments 1 and 2, between experiments 1 and 2, we double the concentration of A. Whereas, what do you notice about B and C? They remain the same, right? So that means that however the rate changes, we can safely assume that this change in rate from 2 times 10 to the negative third molar per second to 8 times 10 to the negative third molar per second, that must be because of that change in A, because it's the only thing that's different between these two experiments. So then we want to ask ourselves, what number are 2, because we doubled the concentration of A, to what power equals 4? Well, 2. So that means this must be second order with respect to A. If we double A, the rate goes 4 times as fast. If we were to instead, say, triple the concentration of A, it would go 3 squared or 9 times as fast, etc., etc., etc. It is an exponential relationship. So A is second order. Now, in the words of the poet and philosopher John Bon Jovi, whoa, we are 1/3 of the way there. Now, let's figure out what order B is. To figure out what order B is, what experiments can we compare? Well, how about these ones? So between 1 and 3, notice that A stays constant, C stays constant. The only thing that changes is that reactant B is tripled. So we made it 3 times as concentrated. And when we tripled it, the rate went from 2 times 10 to the negative third all the way up to 2 times 10 to the negative third. Oh, there was no change. Oh, what does that mean? Well, B must be 0th order. We can do whatever we want to the concentration of B. It is not going to change the overall reaction rate. Now then, we've got one more thing that we need to figure out. We need to find the order of C so that we're done with this problem. So, just going to get rid of these annotations here. And let's explore C. So, to figure out what order C is, let's compare experiments 3 and 4. Because A is held constant, and B is held constant, and C is, oh, this is exciting, so C is tripled. We make it 3 times as concentrated. And notice that when we made it 3 times as concentrated, the rate went 3 times as fast. It is a directly proportional relationship. So, if we consider what happened to the rate, it went 3 times as fast when we tripled the concentration of C. What 3 to what power equals 3? Well, just 1. So, this is first order with respect to C. So here is our overall rate law, and any number to the 0th power is just 1, so we can get rid of the B to the 0th. So we can simplify this and just make it here, choice D. Okay, in this problem, we're looking at the spoilage of fish due to Pseudomonas bacteria. So, we're told here that the activation energy of this reaction is 80 kilojoules per mole. We're also trying to figure out how many times faster it happens at 26 degrees Celsius than at 4 degrees Celsius. So we want to see how many times faster it is if we leave it lying out in a balmy room rather than in a standard refrigerator. So anytime you want to compare how much faster a reaction goes at one temperature than the other, there's an equation for that. And the equation that we'll use for any problem like this is the natural log of K1 divided by K2 equals activation energy divided by R times 1 divided by T2 minus 1 divided by T1. And I honestly think this is the most ghastly equation that we use this entire semester, and it's really not that bad as long as we stay organized. So I want to emphasize the most important thing here is to just make sure that you're keeping consistent with your temperatures and rate constants. So what I always like to do is I always like to start by writing T1 equals the higher temperature. Because these questions are generally speaking always worded how many times faster is a reaction at one temperature than another. So what we're actually solving for is this ratio of K1 divided by K2. Since we want to know how many times faster the reaction is, reactions will always be faster at higher temperatures. So by setting T1 as the higher temperature, we ensure that K1 is the larger rate constant. So T1 is 26 degrees Celsius, which we want to convert this to Kelvin, so add 273 to it. So this is equal to 200 299 Kelvin. Cool. So T2 will be our lower temperature, which is equal to 4 degrees Celsius, which if we add 273 to that is 277 K. Okay, now we're going to plug in. We're just going to make sure that we're consistent with our units. And let's do this. So the natural log of K1 divided by K2 is equal to our activation energy, which is 80 kilojoules per mole, divided by R. So we just need to make sure that our units align here. So 0.008314 kilojoules per mole Kelvin. You could also instead convert the 80 kilojoules into 80,000 joules and use 8.314 joules per mole Kelvin. Doesn't matter as long as you are consistent with your units here. Okay, and then the two numbers that we're going to be plugging in. So we have 1 divided by T2, which is our lower temperature. So it's 277 K. Minus 1 divided by our higher temperature, which is that 299 K. And now, my second biggest recommendation for this is do not be a calculator superhero. Don't try to do this all in one fell swoop. First thing I like to do is I like to get rid of the stuff in the parentheses over here. So I'm going to do 1 divided by 277K minus 1 divided by 299K. So that equals 0.000266 Kelvin to the negative 1. Cool. Everything else, we haven't done anything else here, so I'm just going to keep everything else consistent. Now we'll multiply the 0.000266 Kelvin to the negative 1 times the 80 kilojoules per mole, divide by the 0.008314 kilojoules per mole, and you'll notice here that something interesting with the units happens. So Kelvin cancels out, and kilojoules cancels out, and moles cancels out, and we're just left with a dimensionless ratio here. So this ends up being, that's 2.56. It's equal to the natural log of K1 divided by K2. We'll just take E to both sides, and that'll get rid of our natural log here. And we'll end up getting that K1 divided by K2 is 12.88. So this would go about 12.9 times faster. So this kind of showcases the importance of keeping things in the refrigerator. The spoilage goes a lot faster if things are held out at room temperature. Okay, in this next question, what we need to do is analyze this reaction profile diagram. And what we need to do is figure out what the rate limiting step is and figure out if it's, well, the question says endothermic or exothermic. This question is actually a relic from when we use that terminology instead of endergonic versus exergonic. Endergonic versus exergonic is technically more accurate because it deals with energy and not just enthalpy. But here, let's just say, for all intents and purposes with this question, exothermic correlates to exergonic, endothermic correlates to endergonic. We'll see that there's also entropy that goes into play later on in the semester, but we haven't gotten there yet. So first, let's figure out energy change. If we draw this baseline here, we can see that the energy change here is, it's a net negative delta E. Okay, so this would be exergonic. Energy is exiting. Or for the case of this problem, we're going to say exothermic. Not technically necessarily true. Could be true, but anywho. And then which of these steps is the rate determining step? So whichever one has the greatest activation energy. There are 3 steps. There's step 1. Each hill represents a step. The one with the greatest height is going to be our rate determining step. So notice that this first step, wow, look at that. That is a large hill that we have to overcome here. That is going to be our answer, actually. This is going to be the slowest step. Whereas if we look at these other 2 steps, this one, that's not that big. And this one, comparatively, also not that big. Step 1 is clearly has the largest activation energy and is therefore the slowest. So the answer is going to be A, exothermic, with the first step being the rate limiting step. Okay, in this problem, we need to identify what catalysts are present and what intermediates are present. Well, what catalysts, if any. So we'll see. So remember that catalysts are kind of opposite of intermediates. So an intermediate is something that's made, it's present for an intermediate amount of time, and then it's used in a subsequent step. Whereas a catalyst is something that is used up in one step and then reproduced in another step. And it doesn't have to be like the first step or the last step. Often is, but not always. So in this case, is there a catalyst? And the answer, despite what this says here, is yes. We can see nitric oxide, NO, is used up in the first step and reproduced in the second step. Anything that's used in one step and then remade in a later step, that's a catalyst, because once it's remade, it can facilitate the reaction over and 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 over again. So our catalyst here is nitric oxide, NO. Now, follow-up question, what are the intermediates of this particular reaction? So I'm going to circle the intermediates. Okay. All right, so NO2, you'll notice, is produced in this step, and then it's used in a subsequent step. So that's an example of an intermediate because it's there for an intermediate amount of time, then it's used up again. Also notice atomic oxygen. Oh, it's produced in this step and then used in step 3. Okay, and I think that about covers it. So our overall reaction is 2 ozones turning into 3 oxygens, O2s, and we have our, again, intermediates are going to be our NO2 and our oxygen. So the answer is B. Okay, in this question, well, first, what we're trying to do is we're trying to figure out how long it's going to take for a reagent to be 75% used up. We need to figure out what order this is going to be in order to relate the initial amount, the final amount, and the amount of time that it takes. So, let's see, what order could this be? Well, if we look at this graph here and we look at the y-axis and the x-axis, we're plotting 1 divided by concentration versus time. That very conveniently matches up with our second order integrated rate law. 1 divided by A sub t is equal to KT plus 1 divided by A sub 0. So our friend the graph enthusiast came along and went, woo, because they saw y equals mx plus b. If you ever plot 1 divided by concentration on the y-axis versus time on the x-axis, and you get a straight line, that means you are dealing with a second order reaction, and the slope is equal to k. So the slope here is our friend the rate constant k. All right, so that means that we're given slope of the trend line. That's just equal to k. Now then, what other information do we know? We're told here that we're starting off with 18 molar of our H2SO4. So A sub t, we want for this to be 75% used up, which means only 25% of it will be remaining. So 0.25 times our A sub 0. We want to know how long it's going to take for it to drop down to 25% of its original concentration. So if we multiply our A sub 0, I'm just going to plug in the 18 molar here. When we do this, we'll end up getting that A sub t equals 4.5 molar. Now we have all the information we need to plug into our our second order integrated rate law. So let's go through and figure out the answer. So 1 divided by A sub t, we're trying to see how long it'll take for this to drop to 4.5 molar, is equal to KT, our K is 0.0333, m to the negative 1, s to the negative 1, times T, which is what we're solving for, plus 1 divided by A sub 0, and our initial concentration is 18 molar. Okay, so now I'm just going to clean this up a little bit. I'm going to do the inverses here. So we get 0.222 molar to negative 1 is equal to, and our K again is 0.0333 molar to the negative 1, S to negative 1, times time, which is what we're solving for here, plus 1 divided by 18 molar, which is 0.0556 molar to negative 1. Now I'm going to subtract this from both sides, and we'll get 0.167 molar to negative 1 is equal to 0.0333 molar to negative 1 s to negative 1. So we'll divide both sides by K, and we'll end up getting our time. So T equals 5.00 seconds. Okay, in this problem, we're dealing with one Dr. Rick T. Catt, a distinguished professor of science with a taste for adventure and a knack for sustainability. Their lab is working on a way of improving the decomposition of a type of plastic, polyethylene terephthalate, aka PET. And what they've done here is they found a way to take the uncatalyzed reaction, which clocks in 46.2 kilojoules per mole. They've been able to drop it down to an impressive 26.2 kilojoules per mole. Cool. We're assuming that the Arrhenius factor A is unchanged by catalysis, often a poor assumption, but one that will make our lives easier when doing the calculation. And then what we're trying to do is see how many times faster the reaction will be with the catalyzed activation energy than the uncatalyzed activation energy at 25 degrees Celsius. So we're going to use this form of the Erroneous equation. Our rate constant is equal to A, E, and then the power of negative activation energy. We're trying to find the ratio of the catalyzed to uncatalyzed, so I'm going to put the CAT there just for catalyzed, divided by RT. Okay, and now what we want is the ratio of the catalyzed to the uncatalyzed. So I'm going to then divide by K uncat for uncatalyzed, which is equal to A E to the negative uncatalyzed activation energy divided by RT. And there are ways that we can simplify this expression here. Honestly, what I like to do is solve for both exponents before plugging in values. I just like to take this very, very slowly. That helps to ensure that the calculations don't get messed up. And the reason why we're keeping A the same is any number divided by itself is just 1. So this helps simplify our calculations here. So I'm going to plug in values. So if e to the negative 26.2 kilojoules per mole, this is at 270, well, no, it says 25 degrees Celsius, which add 273 to that, so it's going to be 298 K. And then R, it needs to be in terms of kilojoules here, so 0.008314 kilojoules per mole Kelvin. Okay. Now let's plug in our corresponding values for K uncat. So it's going to be equal to E to the negative activation energy, which is 46.2 kilojoules per mole. Divided by RT. Again, our temperature is 298 K. And our constant is 0.008314 kilojoules per mole Kelvin. Okay, and kilojoules per mole Kelvin, this will all cancel out, so the kilojoules, the moles, and the Kelvin. So now I like to simplify these before going any further. So we get k cat is equal to e is 10 to the negative, or e to the negative 10.57, and we'll divide then by k uncat. That's negative 18.65. And then when we solve, we'll end up getting that this ratio is 3,230. So lowering activation energy has a pretty profound impact on how fast a reaction goes. Thanks, Catalyst. Thanks, Dr. Rick T. Cat. So in this question, we're trying to figure out what order a given reactant is. And we're plotting concentration versus time. So probably the best way of analyzing this is to see if the half-lives are consistent with respect to each other. So if we're starting off with 40 molar, our first half-life would take place when we get down to 20 molar. So let's see how long that takes. Okay. So it looks like here, this half-life took about, I'm going to say 0.7 seconds or so. Give or take. Now then, what we want to do is see how long it takes for a subsequent half-life to occur. So that would be the time it takes to go from 20 molar down to 10 molar. So let's see, we hit 10 molar at, appears to be a total of 1.4 seconds here. It's about the 1.4 second mark. So it looks like our second half-life, that was the time that it took to go from 0.7 to 1.4 seconds. So our second half-life was also equal to 0.7 seconds. Now, if you look at this, these are consistent with each other. Consistent half-lives are a hallmark of what order of kinetics? You only get consistent half-lives with first order, because half-life is only dependent on the rate constant k, 0.693 divided by k. So if we want to find k, we can actually rearrange this equation. K is equal to 0.693 divided by 0.7 seconds. And this is going to be about equal to 1.0 seconds to the negative 1. And we are done. So this is a first order reaction. So rate is equal to k times a to the first. And the value of the rate constant is 1 second to the negative 1. So the answer is A. In this question, we want to find the average rate of appearance of B between time equals 10 minutes and time equals 30 minutes. So we're trying to find average rate. We're given all these different time points. We're only actually interested in the 10-minute mark and the 30-minute mark. So I'm actually going to scratch some things out because I don't need any of this information. We're not concerned with time 0 or 20 minutes or 40 minutes. Okay, so remember, a rate is a change. We're looking at the change in the concentration of B over the change in time. And we actually already know the change in time. So if we're going from 10 minutes to 30 minutes, that means dt is equal to, so from 10 to 30, that's 20 minutes. Now we just need to make sure that our units are consistent. Notice how all of our answers are in molarity per second. So I'm going to turn this minutes. For every 1 minute, there are 60 seconds. So this is 1,200 seconds. Okay, so we know dt. Now, it's our goal to figure out how much B appears during that time. And something else to note, notice that the units are 0.065 moles of A. But we want to find, again, if we look at the units of our answers, we're looking for molarity, not moles. So what I'm going to do first, actually, is I'm going to use the fact that's a 100 milliliter flask. 100 milliliters, so divided by 1,000 milliliters for every 1 liter is equal to 0.1 liter. And all I'm going to do is take, actually I'm going to find the change in moles first. I think that's going to be simpler. So the change in moles in A are, so So the change in A, we end with 0.036 mole. Between those two times, we started with 0.051 mole, which gives us that the change in A is equal to 0.015 molar. And that's negative just to show that it's disappearing. But rates never have negative signs in it, so you would just say that it's the 0.015 molar that disappeared. Oops, sorry, 0.015, not molar. Moles. We have not converted it into molarity yet. But now let's do that. So this is divided by the 0.100 liters that we have. So this ends up equaling that the molarity of A that changed was, so again, the change is negative, but I'm not going to include the negative sign here because we're just looking for the rate. The negative just shows us that it's what's disappearing. So 0.15 molar of A. But we're not interested in A. We're interested in B here. Now we can just use the stoichiometric coefficients from our reaction. That's up here. And we can see that for every 1 molar of A that we use up, we end up producing 3 molar of B, which means that the change in B, change in the concentration of B, is equal to 0.45 molar. That's how many molar of B would have appeared during that time. So now I'm just going to turn this into a rate. So I'm going to divide by the amount of time, the dt, 1,200 seconds, and we will get our answer. So we end up getting 3.75 times 10 to the negative 4th molar per second, which rounds to choice D.